Welcome to The Explainer. Today, we're diving deep into the scientific methodology of the energetic paradigm. We're going to unpack exactly why discovering what sustains a system is literally the only way to truly understand it. Now, the energetic paradigm isn't just a shiny new set of buzzwords or some abstract metaphor. It's a fundamental shift in how we identify problems, generate hypotheses, and correct errors. And its central claim, it's incredibly straightforward. Absolutely nothing persists merely because it exists. Here's our roadmap for today. We'll breeze through surface versus structural analysis, explaining system persistence, constraints and hidden costs, testing explanatory power, the role of time, and finally, we'll wrap it all up with a 10-step scientific procedure. Let's get right into it. Starting off with Section 1, surface versus structural analysis, and how we need to shift the very first question we ask. When we usually try to figure out a problem, conventional analysis has us starting with questions like, what just happened? Or what variables are correlated here? We tend to stare at a symptom and just try our hardest to squash it. But the energetic paradigm, it hunts for the underlying maintenance structure. It asks, what is continuously maintaining this state? This distinction is an absolute game changer. A visible event might be a temporary blip, but a sustaining mechanism is what makes that same event rear its head over and over again. Think about it. If a policy just suppresses a behavior without actually changing the underlying incentives, that exact same energy will just redirect into another channel. So if you anchor just one crucial point in your mind right now, make it this mantra. State is what we observe. Maintenance is what keeps it from dissolving. A disease persists because a hidden mechanism is actively recreating that pathological state. A specific market structure persists because capital, regulations, or network effects are actively protecting it. A scientific explanation is entirely incomplete until it puts a finger on exactly what is keeping the phenomenon alive. Moving right along to Section 2, explaining system persistence, which covers the first two principles of our methodology. Principle 1 is all about explaining persistence. We see theories all the time that are fantastic at explaining how, say, a disease or a corporate monopoly got started, but they totally miss the mark on what inputs or feedback loops are continuously sustaining that condition today. Sure, a company might have gained market power from an early, genius innovation, but that doesn't explain why competitors can't displace it right now. An origin story is great for a superhero movie, but it's pretty terrible for structural analysis. To get a dynamic explanation, we really have to ask which actors are benefiting from this continuing, and which alternative states have suddenly become way too expensive to reach. Then we hit Principle 2, which urges us to identify the reproductive mechanism. Let's take an AI model as an example. The model has a bias. It then generates bias data. That data is turned right around and used for the next training cycle, and suddenly, the next model reproduces that bias even more strongly. The big discovery here isn't just that the bias exists, it's that the bias has entered a loop where it reproduces itself. You see this everywhere. It's like a bureaucracy that keeps expanding simply to manage the massive complexity it just created for itself. That brings us to Section 3, constraints and hidden costs, diving into Principles 3 and 4. Principle 3 brings us face-to-face with the binding constraint. Look, systems don't just behave based on unlimited good intentions, right? They operate within strict, hard limits, like energy, time, capital, or just human coordination ability. The binding constraint is the absolute limit that dictates what the system can actually do right now. You might throw a dozen more employees at a failing project, but if clear coordination is the actual binding constraint, the system is just going to reorganize itself around that stubborn bottleneck, and you gain zero efficiency. We must always ask ourselves what resource would still hold us back, even if every other resource magically increased. And Principle 4, this one reveals a fascinating, tricky truth about false progress. You've got to track where the cost goes. So often, what we call improvement is really just relocating the damage. A model becomes more accurate, great, but the computation cost explodes. A company becomes super internally efficient, but wait, they've just shoved all their risk onto their suppliers. The measured variable looks fantastic on a chart, but the total system hasn't actually improved at all. For every claimed advancement, the energetic paradigm demands we ask, what was consumed, who absorbed the new burden, and what future obligation was secretly created? All right, let's look at Section 4, testing explanatory power. These are Principles 5 through 8. Principle 5 is our reality check. It demands we test whether a new state can actually sustain itself. A temporary patch is not structural change.
Think about weakly stable states, like an AI model that only acts aligned when it's being constantly babysat by human monitors, or a medical treatment that only works as long as the dosage keeps climbing. The second that supervision ends, the whole thing collapses. The true test of any real intervention is, does the improvement survive after you take away the external support? Has the underlying regenerative mechanism actually changed?
Principle 6 tells us to look for structural compression. A really solid scientific theory explains a ton of observations through one very compact mechanism. Now, keep in mind, we aren't just rewarding simplicity here. An explanation can be simple just because it ignores all the messy complexity. What we want is structural compression. So if one underlying instability in an AI's memory architecture perfectly explains 5 seemingly independent bugs, that structural compression proves you've likely found the true mechanism, which saves you from playing endless whack-a-mole with localized repairs.
Now, principles 7 and 8 draw a hard line in the sand between actual science and mere ideology. Your evidence has to discriminate, not just confirm what you already believe. If your proposed mechanism isn't vulnerable to evidence that could prove it flat out wrong, you're dealing with ideology. We have to generate distinguishing predictions. What should we expect to see? And honestly, more importantly, what should absolutely not occur? We have to ruthlessly comparing competing explanations, not just hunt for data that backs up our favorite idea. What intervention affects one mechanism but completely ignores another? That is exactly how we defeat confirmation bias.
Next up is Section 5, the role of time, diving into Principles 9 and 10.
Principle 9 is a big one. You must separate local improvement from system improvement. We have all seen this happen, right? One team brilliantly optimizes their own workflow, but they accidentally triple the workload for another department down the hall. Actors are constantly optimizing metrics at the specific level where they personally benefit while entirely transferring the hidden failure to the larger system. You simply don't understand a result until its consequences across all levels, from the component to the agent to the institution and the long-term environment, are carefully traced.
Principle 10 shows us that time itself is literally a part of the mechanism. Small changes snowball. A tiny, minor error on day 1 can constrain later possibilities, eventually becoming baseline training data, and by year 10, it locks in with a massive reversal cost. The energetic paradigm doesn't just judge an action by its immediate slashy output today, it examines how that action fundamentally changes the system's future capacity to adapt tomorrow. Which finally brings us to Section 6, the 10-step scientific procedure. At the absolute core of this entire framework is one huge driving question. It completely replaces our normal everyday obsession with mere surface events. The goal of this scientific method isn't to just make everything sound like an energy problem. The goal is to ruthlessly discover the exact mechanisms that make systems persist, change, fail, recover, and evolve. So here's how the first half of this procedure plays out in reality. Step 1, you define the phenomenon precisely, no vague terms. From there, Step 2 requires you to separate the visible state from its hidden maintenance mechanism. Then, in Steps 3 and 4, you actually map out the flows of resources and hunt down those sneaky reproductive feedback loops. Finally, Step 5, locate the true binding constraint. Doing this sets a rock-solid foundation, pulling us past the distracting symptoms and straight into the system's structural reality. Then, the second half pivots to hardcore scientific testing. Step 6 compares competing mechanisms, which naturally allows you in Step 7 to derive those distinguishing predictions we talked about. Once you have those, Step 8 is designing interventions that target the mechanism, not the symptom. Step 9 observes if the state actually persists without external life support. And Step 10? It's the hardest part, humbly revising your model when the evidence inevitably proves you wrong. This 10-step loop forces you to intervene at the structural level and guarantees you aren't just slapping on a temporary patch. Because look, if you ignore this methodology, you're pretty much doomed to rely on weak interventions. A weak intervention only changes the visible output. It requires permanent external life support. And worst of all, it usually just transfers the cost somewhere else, creating a hidden future obligation that will inevitably come back around to break the system later. So I'm going to leave you with this provocative thought to chew on and apply to your own analysis right now. When you look at the stubborn problems in your organization, your code, or frankly your life, are you actually changing the underlying mechanism that reproduces the problem? Or are you just efficiently optimizing a symptom? Think about that and start looking for those maintenance structures. Thanks so much for joining me on this explainer, and I'll catch you on the next one.